we're finishing up our first order differential equations. And so last time we talked about some population models, which really was a chance for us to see applications and do word problems. And who doesn't love a good word problem? And today is going to be a little bit more interesting because I really like to say today is more about qualitative stuff. We're not going to be solving differential equations per se. What we're going to talk about is what's the behavior of the differential equation. In other words, what should be happening without actually solving. And so we're going to be focusing on a particular type. So it's called an autonomous. And so an autonomous differential equation is one which you can write as y prime equals some function of y. So here, the auto is basically self. So y prime is just a function of that its own thing, y. So there's no t or x or whatever the external variable is. And as I said, even if we can't find the explicit solutions, we can think about the long-term behavior. And so how does this work? Well, as we go through our discussion here, you're probably going to be sitting there and thinking, a thought will be emerging. And you're going to be thinking something like, this seems a lot like the first derivative test. So if you put back on your Calc 1 hats and say, hey, I remember this thing called the first derivative test, it seems very much like this. And in some sense, there are some similarities. So how does it work? Well, we look for a couple of things. So the first thing we look for are what we call critical points, and that's where this function over on the right-hand side equals 0. Now, why do we care about these? Well, suppose we have f of a equals 0. So in other words, we have a root, if you like. And then consider the function y equals a. So this I'm thinking of as a function. Well, what's the derivative of a constant? 0. What happens when I plug in a into f? Hint, I'm pointing at it. I'm now circling it. Yeah, it gets 0. Good, good. Okay. That means it's a solution. So critical points are solutions. In fact, they're what we call constant solutions, which means they don't change. So that says, okay, so great. You can find constant solutions. But what about those constant solutions? And how does the curve behave in between? Well, in essence, if you think back to first derivative test, you would say, oh, in between, the derivative would have one of two types of behavior. Either it was positive or it was negative. And we're going to have the same thing here. And positive and negative indicate direction of change. In some sense, you can think of positive and negative as being orientations on the line, where positive means going up and negative means going down. That's actually a great intuition to have. So you say, okay, so what happens? Well, we want to talk about these critical points in terms of classifying. And there's a couple different ways they could be classified. So stable is the first thing. And the picture here of what a stable critical point would look like is you'd have a constant solution A. And the point here is that if you're near A, you get closer to A. So it's like drawing things in, so that the behavior on both the top side and bottom side is moving towards A. Now, nothing ever hits A. Solutions won't overlap, but they'll approach. So this is the stable situation. And then you say, okay, well, what's next? Well, the next one is unstable, so not stable. Well, it's not so hard to imagine what that would be. Say, look, what's the opposite of getting closer? Well, it's getting further away. And so in that case, what solutions will do is even if you're near A, you move away. So you're repelling things. So that's what happens? People move away. Just like when you tell someone you're an art history major, they move away from you. Sorry, let me see. No. People love art history majors. They're great to hang out with. All right, and the last one is semi-stable. Now, you think semi-stable, well, that's like half stable, right? And yeah, that's the idea. So semi-stable says what? Well, what you do is on one side, you're getting closer, and then on the other side, you're moving away. Now, of course, there's another variation as well. I won't draw all the variations here. But how do we know? How do we know what's going on? So, the idea is that we can construct, I skipped here, something called a phase diagram. Now, this is where we get really close to the first derivative test. So a phase diagram is you draw the line, and this represents your y. Okay, so you draw your axis. So this is our phase diagram. And then you mark critical points. Okay, that's no surprising. Do you remember what happened next with the first derivative test? If you remember, what was the next thing? You'd draw the line, you'd mark the critical points, and then what would you do? Choose points in between and? What do you do with those points in between? You plug in. And in particular, you plug it into f of y and ask the question, is it positive or negative? And so we might have something that looks like this. Say, we'll make things up here. So let's say y prime is, y prime is negative. Y prime still stays negative. That's a possibility. Y prime goes to positive, and y prime goes back to negative. Okay. Now, how do we translate information from our phase diagram to classifying stability? Well, let's think about what that means. So suppose, let's start with the y prime greater than 0. If your derivative is positive, what does that tell you about y? What is it doing? It's increasing. It's going up, or for us, since we've drawn it horizontally, that means we're moving to the right. If y prime is negative, what's happening to your values of y? They're decreasing. They're getting smaller. A negative change thinks y is getting smaller. In terms of our diagram, which way do we move? To the left, to the left. When the derivative is negative, we move to the left. Right? That's right. Good. Now, let's talk about these points. We'll start here on the right. Notice, here is my critical point. If I'm near my critical point, am I moving towards it or away from it or half and half? Towards it. Because look at the arrows. The arrows tell the story. We're moving towards. So, is this stable, unstable, or semi-stable? Stable. So if you move towards, you're stable. So that's what it would translate into. Now, let's come here. Another critical point. If I'm near this critical point, am I moving towards it or away from it? Away, because the arrows tell the story. Go away. Go away. So what kind of critical point is that? Unstable. So, all right, great. That's an unstable. So that's the local behavior. Now this last one. What's happening here? It's kind of mixed. On one direction, I'm getting closer The other direction, I'm moving away. So what do we call that? Semi-stable. So this one goes there. So that by drawing this phase diagram, so this is the phase diagram, this picture right here. Drawing this phase diagram, we can tell how the function moves. And that helps us whether things are going towards points, going away from points, or half and half. All right, so that's the main thing for today, most of the theory. Any questions on this idea? Because most of the rest of today is practice. All right. Well, not seeing questions right now, we'll move to practice. Example. For the differential equation y prime equals y squared times y minus 3 times y plus 1, find all of the critical points. Not just some, not just one, all of them. All of them. Okay. And we're going to classify each critical point as stable, unstable, semi-stable. We're going to draw the phase diagram, and we're going to do a rough sketch of some typical curves. So this part right here, the rough sketch, we haven't talked about that, but it'll become, well, we'll work through it. We'll figure it out. We're good. We can do this. We can do this. Okay, so suppose we start doing these things. What would be our procedure to find the critical points?
Say y prime equals to 0.
Yeah, we're going to set the y prime equals to 0. In particular, we set the y squared times y minus 3 times y plus 1 equals 0. And they were even nice to us. They factored for us. Sometimes they're not so nice. That's all right. Okay, so when does y squared times y minus 3 times y plus 1 equal 0? Now y equals 0 at 3 and negative 1. All right, so our critical points are going to be those values. And I'll arrange them in order from smallest to largest. So negative 1, 0, 3. So that was part of the question. We already did it. That doesn't seem so bad, this stuff. Then there's the classify. And then it says draw the phase diagram. Well, we can do it in the opposite order, because I think drawing the phase diagram is a little bit easier than classifying. Or rather, I should say, it's very easy to classify once you have that phase diagram. All right, so we draw the line for y. We've marked the points. We just have to make sure we have them in the right relative order. They don't have to be spaced properly. You can space them properly if you want, but that's not so important. We really just care about how it's splitting up. And in particular, we have 3 points. It breaks the line into 4 pieces. Okay. What comes next? Plug in points. Right. So we pick points. And we can't pick these points. We have to pick points away from there. All right, so pick something bigger than 3. Okay. You could have picked 100. Could have picked 1,000,000. Could have picked 7. But you picked 4 because you're like, let's just pick an easy number. That's a good philosophy. Pick an easy number. And keep in mind, do we care about the value or the sign? The sign, yes. We saw the sign, and it'll open up our eyes when we see the sign. So don't stress too much about like, oh, I got to get this number exactly right. It's like, no, just what's the sign? Okay, so work it through. And we're plugging into this y squared times y minus 3 times y plus 1. Okay, so 4 squared, 4 minus 3, 4 plus 1. All these terms will be positive, positive, positive. So what does that say about y prime? Y prime is positive. Now, I like to draw an arrow, so I'll draw it underneath just to emphasize. So positive means y is increasing. Increasing means to the right. Okay, pick a point between 0 and 3.
1.
1, classic. Classic. All right, 1 squared, positive. 1 minus 3, negative. 1 plus 1, positive. So, positive times positive, what's the sign? Negative. Which way do we move? To the left. To the left. Okay, between negative 1 and 0. Negative a half. Great choice. Negative a half squared, is that positive or negative? Positive. Negative a half minus 3? Negative. Negative a half plus 1? Positive. Positive, negative, positive. So it's negative. All right. So we're moving in that direction. Again to the left. Okay, something below negative 1. Negative 2, great choice. Negative 2 squared? 4, positive. Negative 2 minus 3? Negative 5 with negative. Negative 2 plus 1? Negative. Positive, negative, negative makes it positive. So, which way do we move? To the right. Positive means we're going up. That means we move to the right. So, here's our phase diagram. So that's part of our answer because they ask us to do a lot of stuff. All right. Now, with the phase diagram, we are ready to jump back and do our quick classify. Okay, so how do we do that? Well, we read it off. So here's the classify. So negative 1, what's happening? Stable, because things are coming towards. Stable, things attract. So, good. What about 0? Semi-stable. So if they both go in the same direction, in this case they both went down, or if they were both going up, that means that you really weren't able to make up your mind in some sense. What about 3? Unstable. Good. See, these problems are great. You're probably like, yes, put this on the test. In fact, let's have all the test questions be this. Well, maybe, but we haven't finished all our examples. We aren't even finished with this problem yet. So the last part is to do a rough sketch. Okay, so here's how I would do a rough sketch. We draw our plane. And I want to be really clear. Do you want to think of y as a function of x or t? It doesn't really matter. X? Okay, so I'm going to put x here. I'm going to put y here. So I'm going to draw solutions. Now, I claim there are 3 solutions which are really easy to draw. What are they? The ones that come from the critical points. Critical points are solutions. And so we have y equals 0 is a solution. Y equals minus 1 is a solution. And I'll even write these down. Y equals 3 is a solution. Okay, so those are easy to draw. So those are some solutions, but we want to get some other ones as well. So imagine, if you will, that we took our phase diagram and just turned it. So we did like that. So we have our minus 1, our 0, and our 3. So I'm just copying my phase diagram. And then what we have are arrows. So for instance, we still have the same arrows as before. So we're going up, and then we're going down, and then we're going down, and then we're going up. So this is the phase diagram copied on the side. And now, once I understand that, the whole picture will become fairly self-working. So let's start at the top. If I'm above 3, what should I do? I should move up. So my curves will do something like this. They'll be moving up from 3. If I'm between 3 and 0, should I be going down or should I be going up? Down. So I should be coming down from 3 and heading in towards 0. Something like that. Now you might be saying, is that exactly right? No, but we're getting rough. See this word rough? It says I don't have to be exactly right, but I just have to get a good idea. Okay, what about between 0 and 1? What's the behavior? Going down again. So I come down off of 0, and then I head in towards 1. What about below, sorry, into negative 1. What about below negative 1? I'm moving up. So my curves will look something like that. Now, one quick question. Suppose I had the real sketch. If I were to translate, so in other words, move the picture a little bit that direction, right? So, like this was our special effects budget. We can do it twice in a semester, because, well, it's easy to recycle. What would the curves do? How would they change? I know that's a very weird question to ask. So if I sort of move in the x direction, how does the picture change? Ooh, somebody said it doesn't. That's a great answer because it's correct. Why doesn't it change? Because what? What doesn't depend on x? Now, y depends on x, but what doesn't depend on x? The y prime. Because it's autonomous, it doesn't matter what your x you start with. So if I start here or if I start over there, in other words, if I just translate my x, it just translates the whole curve. So that the picture, if you do a shift in the horizontal direction, it won't change anything. So that's the consequence of being autonomous. So anyways, when it asks for rough sketches, basically all you have to think about is, where am I moving to? Am I going up or am I going down? And then once you know that, there's the picture. All right, good. That was a little bit on the harder part, just because we hadn't talked about how to make a rough sketch. Any questions? No? Okay. So our next problem. Find all critical points for the ODE. Remember, ODE stands for differential equation. The O is for ordinary. dy dt equals 3y squared minus y cubed. Determine whether each critical point is stable, unstable, or semi-stable. Sketch the phase diagram. If y of minus 2 equals 1, what is the limit as t goes to infinity of y of t? Starting this problem, what's something we can do? Well, we really care about this function. It's an autonomous differential equation. So the good thing is we don't have to solve it, but we have to do something. And since it's a polynomial, probably the easiest thing to do is try to factor. This is factor. As what? Y squared times y minus 3. So our critical points would be, well, where the y squared times y minus 3 equals 0, which is 0 and 3. Oh, 3 minus y. But it's still a true statement. Critical points 0 and 3. Okay. Phase diagram. Mark the 0, mark the 3. Okay. So, if you plug in a number bigger than 3, what's happening? Yeah, so if I plug in like 4, why did I put y minus 3? Up here. If I plug in 4, you get a negative times a positive. So y prime negative, moving down. Between 0 and 3, what's happening? It's positive. So we move up. If I'm below 0, what's happening? Positive. So moving up. Okay, so there's the phase diagram. Let's sketch the phase diagram. So classifying, what is 0? Semi-stable. And what is 3? 3 is stable. Okay, so life is good. The only thing left is the question, y of minus 2 equals 1. So we have an initial condition. What's the long-term behavior for y? All right. So how do we figure that out? And in particular, how do we use the phase diagram to figure it out? We could sketch typical curves, but actually we can find it from the phase diagram. So let me ask you a question. In the phase diagram, do I care about the point -2 or 1? Or is it -2? 1 is correct. Yes, why is it 1? Because the phase diagram is attached to the variable y. So 1 is a y value. -2 is your input value. That's a t value in this case. So if I'm using the phase diagram, I go with the y value, not the t value. So I'm starting here. This is where 1 is. Now look at the phase diagram. What's going to happen? What does it tell me, the phase diagram? Between 0 and 3, you move up to where? You're going to keep going until you get close to 3. So the limit as t goes to infinity of y of t is 3. So it comes off the phase diagram. So once you know what your initial y value is, just wherever the interval is, follow the arrow to your next critical point. Now, it may be the case that follow the arrow takes us to infinity. That's fine. Then the answer is infinity. But once you know your initial value, just follow the arrow. It'll tell you where you end up in the long run. All right. So that's that. All right. Good. A question? Yes?
Let's just say negative 1, right? Does it go to 0 or does it go to 3?
So it will go to 0. So the thing is, it's approaching 0. It never gets to 0. And so, in some sense, 0, these are 0 and 3 are acting like walls, if you will. You can get close, but you'll never get on it, and you'll never get past it. So yeah, you follow the arrow to the next critical point. Other questions? All right. Consider the differential equation y prime equals f of y, where f of y is shown in the picture below. So now you don't get a function like an algebraic expression. You have a function like a picture. Find all critical points, also known as constant solutions, for the differential equation. Sketch the phase diagram, classify each critical point as stable, unstable, or semi-stable, and give a rough sketch of several solutions for the differential equation. Okay. So, one might say, do we just figure out what this function is? No, too much work. We have the picture. We'll use the picture. So here's how I would approach the problem. I'm going to draw the phase diagram. Just right underneath. Where do you find critical points? Y prime equals 0, which would be f of y equals 0. In terms of the diagram, what are you looking for? Be careful. Where are we looking for? Y prime equals 0 means f of y equals 0. F of y equals 0 means what?
Where it crosses 0, or the axis.
Someone said where it crosses 0?
Maximum and the minimum.
You have to be careful here about max and mins. So So remember, this is f of y. So f of y being 0 says I have, when I plug in my point, I get 0. So it's where you hit the axis. So that says you can find your critical points by just looking for where you hit on the axis. Okay. There's a negative there I forgot to copy. So those are our critical points. We're already pretty good. We found our critical points. Now, the harder question. What's the behavior below -3? What's happening? Am I moving to the right, to the left? How do I know? To the left? Are you sure? You're right. It is to the left. How do we know? Because f of y is negative. So where the function's below the axis, that's where f of y is negative, which means y prime is negative. So that's where we move to the left. So we see it's below the axis over here as well. So that will also be a place where we move to the left. What about between -3 and -1? F of y is positive, and so we move which direction? To the right. By just checking to see the sign. Okay, so -3. What can you say about it? Unstable. -1. What can you say about that? Semi-stable. You just follow the arrows. 2. Stable. And look at all of that. We've got the critical points, the phase diagram, the classification. We're in great shape. What's left? Well, the rough sketch. Okay, so for that, we're going to have, I don't know what our variable here is, x and y. So part of this that's going to make it weird is like, notice here, y is on the horizontal axis. Now it's over here, it's x on the horizontal axis. So you have to keep in mind your picture, what's being represented. So I would do the same thing as before, which is just put your diagram, turn it on the side, so you have -3, -1, and 2. And let's see, what do we have? We have do-doot, 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 do-doot. Okay, so I've just copied the phase diagram onto the side. So it's just pick up, put down. All right, what are the easy curves to draw? The constant solutions. Your critical points are easy to sketch in. They just become horizontal lines. And then for the rest, we just need to know which direction we need to go. So if I'm above 2, I'm going down. So I sketch curves going down. Between -1 and 2, going up. So we sketch curves going up. Between -3 and -1, going up again. Below -3, we're going down. And we're done. So once you have that phase diagram, copy it, mark your constant solutions, and then just say, am I going up or am I going down? And then you'll know how to draw it. Yes?
Would your rough sketch be wrong if you only drew one line for like each section?
Well, if I was going to grade, I would be very explicit about what I wanted. I think if you only drew one for each interval, I'd be happy. If you only do like, hey, y equals -1, there's one solution. That's really, really rough. Too rough. I want less rough than that. All right. Okay. So, another problem. Wow, tons of problems today. So you're going to be like really ready for this stuff come the exam or quiz or whenever it is that you need to apply yourself. So suppose you let y prime equal negative absolute value of y squared minus 1 arctangent of y. Then there's part A, find all the critical points. Well, let's just go through and figure this out while we're working it. So this expression over here, this is our f of y. If we were looking for critical points, we're looking for zeros. What values of y make this 0? People have said 1 and 0. Any others? Negative 1. Ah, right, because there's a square there. Right? Any others? Good. Those are the only ones. Okay, so those are our critical points. So the plus minus 1 is what makes the y squared minus 1 0. 0 is what makes arctangent 0. Part B, draw the phase diagram. Okay, well, there's only 3 points to mark for critical points. And a couple of things to observe. There's a minus sign. Well, that's always negative. What about this absolute value y squared minus 1? What can you say about that? It's always positive, except at these 2 points. But the moral is it's never negative. So it's a negative and a positive. So the arctangent y, what about that? Well, what happens above 0 to arctangent? Do people not know arctangent? How could you have gone through 3 semesters of calculus, watching my videos, knowing that someday you'd have to have a reckoning and be like, someday I know I'm going to be in the same space as Steve. I've got to know what arctangent looks like. So, arctangent looks like what? Looks like that. So it crosses at 0, it approaches pi halves as we go to infinity, approaches negative pi halves as we go to minus infinity. Okay. All right, good. Now that we've had our discussion about arctangent, there's going to be a beautiful thing that happens, by the way. I mean, I know I'm like 6 weeks away from it, maybe even 7, but I'm like so excited. There's going to be a cool day when we're going to pull arctangent out, and it's just going to blow our minds. It's going to be like, what? How is this possible? Arctangent, you're awesome. Okay, but that's down the road. I could just like feel it though in the future. It's just like sending awesome waves back just because of how cool it's going to be. Okay, all right. So, moral of the story. If y is positive, arctangent is positive. If y is negative, arctangent is negative. So, above 0, what's going to happen? Yeah, this part will always be positive. This part will always be positive, so it's the minus sign. So y prime is positive, me negative. So we're moving down. Below 0, what happens to arctangent? Negative. Negative, negative, positive. So now I can say positive, we're moving up. All right, so there's our phase diagram. Okay, so classification. What can we say about negative 1? What kind of point? Semi-stable. What can we say about 0? Stable. What can we say about 1? Semi-stable. All right. See, we're already like A, B, C. Boom, boom, boom. Okay, now, for each critical point, determine all the initial choices for y, for which the solution to the ODE will, with your initial condition, y is 0 equals y naught, will have y approach the critical point as x goes to infinity. Wow. That's a lot to process. Okay, what is this saying? Well, this goes back to one of our earlier examples where we said, oh, if y of minus 2 equals 1, I don't care about the minus 2. But we said the initial value is 1. What happened in the long run? It drifted up to 3. So what the question here says, look, any initial value, you will either head off towards an infinity or head in towards a critical point. So the question is, if I tell you initial value, how do I know? Well, you figure out where it is and you follow the arrow. So, for instance, if I'm here, above 1, what happens? I move to 1. If I'm at 1, what happens?
Stay at 1.
You stay at 1, because 1 is a constant solution. I won't change. So if I'm anything above 1 or equal to 1, I go towards 1. What if I'm between 0 and 1? I go to 0. What if I'm at 0.99999? Yeah, still go to 0. Doesn't. As soon as I move just even the teeniest, tiniest bit off 1, off to 0. If I start at 0, where do I go? 0. What if I'm over between minus 1 and 0? Go to 0. What about minus 0.999999? Really close. Go to 0. It might take me a little bit, minus 1 might be very persuasive, but eventually I'll leave there. If I start at negative 1, I stay. If I start below negative 1, I drift towards negative 1. Now, we've just talked through the reasoning about the answer, but we didn't say what the answer was. So, if I want to end up at the 3 critical points, so if I want to end up at 1, where do I need to start? Anything at or above 1. So we could write it as a 1 comma infinity, or we could just say y naught greater than or equal to 1. So if my initial condition is anywhere inside of this interval, in the long run I'll go to 1. What about 0? If I want to end up at 0, where should I start? Anywhere between negative 1 and positive 1, but not at those points. So anything from negative 1 to positive 1. Or we could write it as negative 1 strictly less than y0, strictly less than 1. If I start anywhere in that interval, I will drift towards 0. The final thing, negative 1. Where should I start? I can start anywhere below here, even up to including that point. So from negative infinity all the way up to negative 1. Or we could write that as y naught less than or equal to minus 1. So that says, look, if I know my initial value, I know my long-term behavior. I'll end up at one of those critical points.